So to start off our unit on acid-base chemistry, we wanted to talk about two of the most common theories of identifying what makes something an acid and what makes something a base. And so that's the Arrhenius acid-base theory and the Bronsted-Lowry acid-base theory. The Arrhenius acid-base theory is kind of the foundation, and that is an acid is anything that produces hydrogen ions in solution, not hydrogen gas, but the hydrogen ion. And a base is anything that produces a hydroxide ion in solution. So off to the right, these two examples, we have something like HCl that's breaking down to form H plus and Cl minus, and that formation of the hydrogen ion is what makes this reactant an acid. And here we've got NaOH breaking down to form sodium ions and hydroxide ions. And that formation of hydroxide ions is what makes NaOH, or sodium hydroxide, a common base. Okay? A lot of what we're going to be looking at throughout this entire unit in acid-base chemistry is the reaction between hydrogen and hydroxide, which is going to be the formation of two hydrogens and one oxygen, or water. A lot of this chemistry takes place in water, so it's that interaction of how things play out against water. Right? The second formula, the second theory for acids and bases is the Bronsted-Lowry acid-base theory, and that is all focusing on how the hydrogen plays out within a reaction. So Bronsted-Lowry's acid-base theory says that an acid is anything that donates a hydrogen ion, and a base is anything that accepts a hydrogen ion. So we're just focusing on what is producing or giving up a hydrogen ion and what is receiving a hydrogen ion. So if we're asked to diagram a reaction involving ammonia, and this is our formula for ammonia, all right, because H2O is water, we're also told that this is a commonly known base. So one of the things that we're going to do is write a capital B under the thing that we can identify as a base. And then by default, because this is an acid-base chemistry, bases react with acids and acids react with bases. In this example, water is going to act as our acid. Okay? So if this is looking at the Bronsted-Lowry acid-base theory, acids are things that donate hydrogen, bases are things that accept hydrogen. So this water is going to give up one of its hydrogen ions, it's got two of them, and give that to NH3. So one of the things that's going to happen is one of those hydrogen ions is now going to add on to NH3, and we're going to form NH4 with that additional plus sign because of the hydrogen positive ion. And if I take a hydrogen away from water, what's left over is one oxygen and one hydrogen, and that is the hydroxide ion. So this is that formation of that hydroxide ion through this reaction, why NH3 is a common base, because it's also producing the hydroxide ion according to the Arrhenius theory. All right, so there's a term that we supply to the products of this type of a reaction, and it's called a conjugate. Okay, so we're going to connect the two nitrogen compounds, and we're going to say that this ammonia, which was a base, now on the product side, we're going to refer to as a conjugate acid. And then the two oxygen-containing compounds, if we link those together, water started as an acid. We're now going to call this a conjugate base, which makes sense because the hydroxide ion was one of our fundamental theories of what makes something a base. Right? So if we were to flip this and put these on the reactant side, this now is going to act as an acid and push that hydrogen back onto the base, reforming the NH3 and the H2O. Okay, so in acid-base chemistry, we're also going to be taking some time to figure out what's actually exchanging in the chemical reaction. Now, going along with the theories of acids and bases, we're going to be talking about some of the properties of acids and bases. So some examples is a nice visual that I pulled off the internet. A lot of fruits have a lot of concentrated like citric acid and things like that. Pineapples, limes, lemons, apples, kiwis. So things that give a really tart, sour flavor are tart and sour because of their acidity. Okay, so some of the properties over here of things that are known acidic. All right, they have a high concentration of hydrogen ion. And so this term, remember, concentration is really referring to the molarity. And there's a simple abbreviation that we're going to write. Instead of writing the word molarity or the word concentration all the time, anytime we're referring to the molarity of a particular substance, we're going to put that in brackets. So H plus in brackets is referring to the molarity of the hydrogen ions. So that number of hydrogen ion moles per liter for anything that is acidic is relatively high, and the concentration or molarity of our hydroxide ions is relatively low. And this again is what makes certain foods taste really sour. So the identification of a substance based on its sour taste could indicate that it's highly acidic. On the contrary, bases are kind of counterpart or in opposition to acids. So bases have low concentrations of hydrogen ions and high concentrations of hydroxide ions. They taste particularly bitter and they feel slippery. It's kind of an interesting byproduct of anytime something that is highly basic or has a high concentration of hydroxide ions, when it comes into contact with the skin, the oils and the fats in your cells react with the hydroxides faster than they do with the hydrogen ions. And one of the byproducts is turning your oils in your skin into soap, which is why anytime you work with concentrated hydroxides, if you get it on your skin, it really feels slippery, like you just got soap all over your hands. So a lot of common bases are household ingredients like baking soda, lye, which is like an old kind of dishwashing ingredient, ammonia, soap, and when it comes to naming acids and bases, there's a couple of general formulas and patterns that we're going to follow, just like we did last semester when we started naming ionic and molecular compounds. So first off, the general formula of all acids are going to follow this HX, where anything that starts with hydrogen and is bonded to either an anion, a negative ion, or a polyatomic, that's what we're going to use to identify that as an acid. So here A starts with hydrogen bonded to fluorine, acid. Starts with hydrogen bonded to the polyatomic nitrate, that's an acid. Starts with potassium, has hydroxide in it, has to be a base. Okay? And there's a little grid here that does a little summary of some of the basic patterns that we're going to see when it comes to naming formulas of an acid. And there's really three simple rules. The first thing we're going to do is identify the proper name for X. Okay, that alone tells us most of what we need to know to correctly name the acid, because the suffix, the ending of your negative ion, based on what that is, it follows this particular pattern. The second thing we're going to do is add the prefix hydro to anything that ends in ide. So add hydro to the start of all ides. And then the last step is to change the suffix based on, again, that ending of that particular negative ion. So anything that ends in IDE, which most ions end in IDE, like the chlorine ion, we call the chloride ion. That's the only time we're going to add hydro to the start of the name of the acid, and then put in the root or the stem of this name, and then it ends in ic. So if we had something like HCl, we would call that hydrochloric, and then always put the word acid. at the end of the name for the acid. Okay? If we had something like SO3 negative 2, which is the sulfite ion, because it doesn't end in IDE, to categorize all the polyatomic acids from the rest, we don't put hydro. So these don't get hydro at all. And so if this was H2SO3, we would just take the stem of the sulfite ion, which is sulf, and we add OUS to it. So this is what we would call sulfurous acid. And then the only other suffix that polyatomics had was something ending in ate, like the nitrate ion, and that HNO3 ending in ate, again, no hydro, but we would take the stem of nitrate and end it in ic instead of OUS to indicate the different suffix. So this would be nitric acid. Okay, so there are 3 acids here. We're going to come back and name those, but we're going to very quickly talk about how we name bases, and then we're going to pause the video and practice those names to see how we do. The general formula for any base, M stands for any metal ion. So most of the periodic table bonded to hydroxide. That's it. You see hydroxide, that we can identify point blank as a base. And naming bases is the same as naming an ionic compound. So if we had something like CaOH2, we see that it's got OH. We see that calcium's a metal, so we would say that that's calcium hydroxide. That's it. That's all we do to name it. There's no suffix changes. There's no prefix changes. So with that being said, I'd like you to pause the video, practice naming these 4 compounds, and then resume the video to see how well you do, and then we'll go into going backwards to go from formula name to the actual formula. All right, so for this first example, we've got HF. So the first thing we want to do is identify the proper name for X. X is whatever hydrogen is bonded to. So the F ion is a -1 charge. And because it's just the fluorine by itself, we call that the fluoride ion. So because F- is fluoride, we're going to follow that pattern for anything that ends in ide. So this acid has to start with hydro, because all ides start with hydro, and then the stem of fluorine, so we'll say fluor, and then all the hydros end in ic, so hydrofluoric acid. Okay? NO3 up here was our nitrate ion, so that's an exact copy from this row up here. No hydro. The stem of nitrate is NITR, or nite, and we're going to end that with ic. So this is just nitric acid. C is a curveball because there's no hydrogen at the start. It's not an acid, so this is a base. So we would identify the name of K, which is potassium, and then label that with hydroxide. So we just call that potassium hydroxide. And then the last one, we've got hydrogen, 2 of them, because SO4, the sulfate ion, is a -2 charge. And so if this is sulfate, just like up here, anything that ends in ate doesn't have the hydro prefix and has to end in ic. So this being different than sulfite means that it's not sulfurous acid, but it's sulfur as the stem, and this one's going to end in ic because sulfate ends in ate. So we're going to call that sulfuric acid. Okay? So the key part to going backwards is we have a lot of clues within the names of our acids and our bases to figure out what is not having hydro here. Tell me about, should it be an element by itself or a polyatomic? And then once we identify what that X should be, we can use its charge to determine the formula. Okay, so we'll do the first one as an example. We've got chromic acid. So there's no hydro and it ends in ic. Well, that's the pattern that we used for any nonmetal ion or polyatomic ion that ends in ate. So really what we are looking for is the chromate ion. And so if we go to our periodic table, and we identify chromate on the periodic table, that's CrO4 with a -2 charge. So this is really CrO4 -2 as the polyatomic in that acid. And because it's a -2 charge, the formula of the acid has to start with hydrogen, and we're going to have two of them to counteract that -2 charge because each hydrogen is +1. Okay? Here we've got iron 2 hydroxide, iron being a transition metal, so that means this is +2. Hydroxide is always a -1, so we would write 1 iron and 2 -1 hydroxides bonded to that. And then here we've got hydroiodic or hydriodic acid. And so because we have that prefix hydro ending in ic, that means that that non-metal root is by itself. There isn't a polyatomic involved. So iodine, being a halogen in group 7, means that as an ion, it's going to be a -1 charge. So we're going to have 1 positive hydrogen to bond to that 1 negative iodine. Lastly, lithium, located in group 1, is a +1 charge. Hydroxide, again, is a -1 charge. So lithium hydroxide has the formula of LiOH.